Okay, good morning, everybody. Thank you for joining. Some feedback probably. No, I think it's another sound. I think the microphone will capture our sound and then record something else. Okay, but it works. But maybe a little bit annoying. Hopefully, it doesn't matter to you. Okay. Uh, Thank you. Uh, Gak mengganggu soalnya. Okay, we can start. I think now. Okay, some technical. Okay, I think, oh, nice. It's much better now, so it doesn't bother us. Okay, good. Again, welcome everybody. We are very happy to welcome our speaker. Apologize if it is if Jean Nelson. Okay, Jean Nelson. Okay, apologize if I pronounce this incorrectly. Jean Nelson. He is a research assistant at Institute of Space and Plasma Studies at National Cheng University, Taiwan. Right. Okay. Very nice. So this is a special moment for us to learn something that's very technical. Maybe many of us are not very familiar with plasma physics, so especially about tokamak. So today, Jean Nelson will discuss about something is very start from the introduction of tokamak, about how the plasma confinement and the relation with how the magnetic field will trap the plasma. Since as we already know that the fusion reactor is, yeah, maybe you can say that's the future and the very clean reactor that we are expected to be able to run maybe in some decades. Now it's still being developed, but the challenge is how to confine the plasma. There's a temperature maybe like a million degrees Celsius, if I'm not mistaken. So there is no material can survive if it is touched with this very hot plasma. So something in the end we have to trap to confine the plasma with magnetic field. However, the interaction is very challenging because the plasma itself has its own charge, since the plasma is a collection of ion and electron. So if the plasma is moving circularly inside the beam line or the circular path, then it will produce the magnetic field. So now today, G. Nelson will give us some review about that. And in the end, there are some maybe like hands-on, some software and some simulation that will be very interesting to us. So I think that's all the introduction from me, and we are very welcome, Jean Nelson, to give the talk. Please give applause to Jean. Okay.
Thank you. Okay, so thank you very much, everyone. Well, there's one little technical detail right now with the screen. But prior to the technical detail being resolved, I'll just give a brief introduction of myself. I want to thank the professor as well. But okay, so the purpose of my talk today is maybe three things. One is introduce the basics of magnetic confinement fusion and how we develop the idea using a basic principle clause, which, let me see here. Okay. Let me see. I think it's an issue from my computer, perhaps. Yes, it stopped sharing. I'm very sorry for this. Okay. Okay. Yes. Okay. So while the screen is loading, I'll give a little bit of an introduction of myself. So personally, right now, I work at National Cheng University in Taiwan. So it's in the southern part of Taiwan. But my background is not in magnetic confinement fusion. my actual background was in the development of devices called gyrotrons. A gyrotron is pretty much a wave amplifier. So if you've ever seen any type of amplifier, kind of like a microwave, but we were working on millimeter waves, and it was more of a simulation type of work, computational physics work. Nonetheless, my main interest was in fusion. So I was able to get a position as a research assistant in this program. And I had already taken some courses previously, but okay, what do I end up doing as a researcher? That's one of the points that I want to get across, because I know that when students go into the physics department, a lot of students have uncertainty about what type of jobs they can get in the future and what type of paths they can follow. It's something that it's a main thing because physics is too broad. So there's this paradox of choice. You have so many choices, so many paths to take. And how do you find one that you like and follow it? Sometimes you can follow it and sometimes it changes. And well, in my case, I kind of found this topic by attending a summer school. And I found it interesting, even though I did not understand anything at the moment, maybe only the basics at the moment, but nonetheless, I found it pretty interesting, and it lighted the spark of curiosity within me. So I became more curious about it. So if you want to keep on going through research, one of the main driving factors for how much you will progress is the curiosity. So curiosity is very important because curiosity will give you the persistence to keep on going with the problem without getting too tired of it. So going back to the main thing, I ended up working as a research assistant on the development of a project called FIRST. It's called the Formosa Integrated Research Spherical Tokamak, and it's a tokamak being developed in Taiwan right now. And I will also showcase the work that I am doing. So keep in mind, my background is more of a computational, theoretical background, but now I'm doing more of an experimentalist work. So I'm still figuring out my path. And I think many students will do somewhat of a random walk before they find the path that suits them. So going to the part of the lecture, I'm going to introduce magnetic confinement fusion. So we're going to start with the magnetic mirror. I will explain the principle of the magnetic mirror, and then how we develop this into a donut-shaped chamber that we call a tokamak. And I will also give some use cases of how I've used AI recently to develop tools that help me visualize more abstract concepts and how to visualize them while keeping the physics there. What I mean is, a lot of the times the AI can hallucinate. It can suffer from hallucinations, and you cannot trust the actual physics. So one of the main things is that you need to use AI as a tool, but you have to know what you're using it for. So you need to understand what you're asking it before you ask it. And that's one of the things that I will showcase here. So what will this lecture give you? Thank you for everyone attending, and thank you for hosting me. It's a privilege for me to be able to give this talk. And if any of you learns at least one thing about it, I have already won. That's a big gain for me. So the structure of this lecture will be, okay, I will introduce the magnetic bottle. So why charged particles can be guided by magnetic fields. This is somewhat a little bit basic. What happens when we put two magnets in a particular configuration and we inject particles in, and we will see how they behave. Following that, we will see how sometimes this configuration can lead to trapped particles. So they will end up bouncing in between one magnet and another. I will showcase it later. Following that, we will see how we close the ends. So kind of like, I think, Pac-Man. So in Pac-Man, when you used to play Pac-Man, once you go out one of the borders, you come back through the other border. So it's kind of like a completely closed surface. So this closed surface brings us some magic. Then I will go into the real machines. That is one of the largest constraints why this topic has been labeled, even some people consider it a joke. And there has always been this running joke that fusion is always 10 years away or 50 years away from realizing it, and it hasn't been realized. Now, that's not to say that there is no progress being done. That's just to say that a lot of people overclaimed results. So that's something very important. If you have results, you only give what you have. You do not give more than what you have. Otherwise, people will lose trust in you. Once people lose trust in you, it's very hard to regain trust. So there's a saying. Think about a bucket. And as you fill this bucket with water, each drop is that trust. Once you build that trust, it only takes one leak for all the trust to go away. So that has been the main problem in this field. Following that, I will show how I have used AI to develop tools that have become useful for me, explain why they are useful, what were the use cases, and also use it as a didactical tool. So fusion requires three things. It requires a very high temperature, 10 to 20 keV. So to have an idea of this, we're dealing with temperatures that are tens to hundreds of millions of degrees on Earth. Why is this? Because we want to mimic the process of the sun, but on Earth. So in the sun is so massive that the gravity actually pushes everything down. It keeps everything so contained. The gravity is so strong that atoms fuse, that atoms undergo fusion and fission. You can start from hydrogen and helium, and slowly you start developing the heavier elements up to the point where you get to iron, where fusion is no longer sustainable, and that's pretty much the life cycle of the star. Then it dies. Now, the main force that is keeping everything together on the sun is gravity. But what's the problem? For gravity, you need mass. There's no way to mimic that force that compresses things the same way that gravity does. But so we need to come up with another way to compress it. And how do we do this? Through magnetic fields. I will explain it briefly. But so we need a chemical reaction. So here is deuterium plus tritium, and we will release an alpha particle. We don't think too much about that right now, and plus a neutron. This neutron will be highly energetic. It will be released, and this neutron will then, we will then use those neutrons that are released, that are highly energetic, to heat up some water, and then the water would just create steam, and at the end of the day, it's just a turbine that's spinning that would generate the electricity. So that's one of the constraints. Another thing is that to make particles, or to make these atoms fuse, we need enough collisions if we want to mimic it. So we need to compress it enough, and we need to have enough atoms that are bumping into one another so that they can eventually, we will have one fusion reaction occur out of maybe 1,000 events. Because once particles get too close together, they will diffract. So there's a reason why we're using deuterium and tritium. It's due to the cross section being able to allow a small chance of fusion to happen. That's the main motivation for that. And following this, we need density, temperature, and we also need to confine it for a long enough time. So then we will show, yes, NT tau. That's the triple product. And all of these three quantities matter. Now, the main thing is that how do we make this work for long enough? So the main problem is the engineering sustaining a favorable power balance and not merely producing one fusion reaction. We need to produce several fusion reactions within a time frame to be able to generate more energy than we have put into it. Now, here is the thing. Why does more energy come out? I think you can recall Einstein's law, E squared equals m squared c to the fourth plus p squared c squared, the full version. So you need enough collisions to create this fusion reaction, and you need enough of these reactions to be able to convert that mass into energy. So rather, right now, instead of converting kind of like energy into mass, we're trying to convert mass back into energy. So that's a very challenging problem. So why is an invisible bottle needed? So the thing is, I was just talking that we need a very high temperature, tens of millions up to 100 million degrees Celsius. It doesn't matter if it's Kelvin at this point because we're measuring the temperature in keV. Now, the thing is, how do we make sure that this material is confined? That's where the magnetic field plays a massive event. So normally, if we have such a hot thing, there's no material on Earth that could sustain it. These are temperatures. To give you an example, the core of the sun is roughly 5,000 degrees. 5,000. And if we're dealing with 1 million, you can think, okay, what type of material can we make this device out of such that it can handle this temperature, right? So, yes. And the other thing is that any material wall would cool and contaminate it. So the energy would be released onto the wall melts, and then the energy just dissipates, right? So the particles must be guided without touching the wall, which is following the magnetic field lines. So charged particles do not move freely across magnetic fields. We call the Lorentz force. The velocity parallel to B, the particle streams along the field line. And the velocity perpendicular to B would give the gyro motion of this particle following the field line. So the trick is to design a useful field line geometry. Now, the way heat is transmitted, you all recall how energy can be transmitted through conduction, convection, and radiation. Now, if we prevent these particles from actually being able to touch the wall, so we make this invisible wall, then we don't have to worry about having such a hot thing within a metal container. Otherwise, it would just melt and it wouldn't work. So we have to have a trick to guide these charged particles in such a way that they're far enough from the wall so that they do not damage the wall. Nonetheless, experimentally speaking, perfect confinement is impossible. There's always losses. Nonetheless, we want to minimize these losses. Going on, Alex, okay, so here is kind of like basics of how this magnetic mirror works. So think about it like this. We have two electromagnets. Here I put north and south just for reference. So you can see that the magnets are aligned in the same way. And we would have a charged particle over here where there is a stronger magnetic field and the weaker magnetic field right in the middle over here. So if we inject a charged particle, it will follow the field line. It'll get into the weaker magnetic field. And if we do it in a particular way, we can actually trap the particle so that it bounces here and the perpendicular velocity is converted to the parallel velocity. Now, let me showcase sorry. Okay. Is it this one? No, wait, here it is. All right. How do I do it? Okay, so here we can see a brief simulation of how the magnetic mirror is working. Sorry for the lag. But we see that here there is two constraints. One is the mirror ratio. The mirror ratio would be the ratio of the maximum magnetic field, which is at these coils over here, and the minimum magnetic field, which is at the center. So as we see over here, we can increase the magnetic mirror ratio, and you'll see that we will actually shorten. Sorry, we should see it in a little bit. We should over here. Okay, yeah. We shorten the path of the, yes, we shorten the path of the reflection. That means if we increase the magnetic mirror ratio, that means that the strong magnetic field is much, much stronger than the weaker part. That means that this charged particle that we injected into this configuration, whether we inject it from here, or we inject it perpendicularly, it would be aligned with the field lines, and it would be trapped. Now that would give us an idea of how much the particle bounce or the amplitude of this bouncing. Following this, we can have the initial pitch angle, which also controls the last cone. So here is a passing particle. This means that, okay, right here, we don't have the proper conditions, which is the mirror ratio, as well as the initial pitch angle, which is the angle between the velocity and the field at the bottle center. So the field at the bottle center would be over here. So it's also dependent on the angle that we injected. So here you can see the particle just comes in through and escapes. Following this, we see that here the particle is trapped. Now, we can think about this. Right now, this is a very simple simulation. So we can see the model boundary. The guidance center is not shown. We're only seeing the gyrocenter radius moving. Because as this particle goes like this, remember that it's also engaging in gyro motion. So it's spinning at the same time as it's following the magnetic field. This is very important. Right now, it's not omitted just for the showcase purposing. And for here, we also have the adiabatic invariance, which is one of the conditions for this model to actually work, that as B rises, conserving it raises the perpendicular energy with total kinetic energy fixed. Parallel speeds fall to 0 at the turning point. So then that means that once the perpendicular energy has been raised to the max. That means we took it from the parallel energy, kinetic energy. And as that falls to zero, then the particle bounces back. So this is the first part. Going back to the presentation, sorry, here it is. By the way, I will upload this simulation to the cloud and everyone can play with it and everyone can study it a little bit more in detail too after the lecture. So let me just move this guy, put it back into full screen. So this principle generates pretty much this magnetic bottle. So this principle generates kind of like gives us an intuition of how particles get trapped. If particles are trapped, they cannot interact with the wall. No matter how energetic they are, they're still trapped. Now, what would happen if from the mirror, we just close the ends? So we make it kind of like into this Pac-Man world. So we grab kind of like this, but we twist it and connect this part to this part. A particle would just keep on spinning, would keep on spinning and spinning and spinning. Now that's the intuition behind the toroidal field coils of the tokamak. These are one set of coils to trap the particle in this way to be able to just circle around. So a tokamak is in the shape of a donut. And the reason why it's in the shape of a donut, we can see the intuition a little bit from here. Are there any questions so far? Any confusions? Any comments? No? Everything okay? All good so far? One guy said good? Okay, thank you. All right. So next, a particle reflects as parallel energy becomes perpendicular energy. So we see the adiabatic invariant. This is one of the mathematical conditions that we need for this device to work. We also have the conservation of energy. We have the parallel slowdown, which here is the perpendicular force is proportional to the, should be the gradient of the magnetic field. And we also have the loss cone boundary. So to give an intuition of the loss cone boundary is like in the simulation before. So sorry about the switching. But over here, wait a bit, it's gonna update. Sorry, my computer is a very basic one, so it takes some time to you know, update. Yeah. No. Actually, my computer is it's a 4 GB RAM computer. so 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 that's that. Just the fact that it's running this simulation, this was completely written in HTML. So that's the only way we can actually run something like this on something like this. Otherwise, I would remote access to my server and then that would show a proper simulation. Okay, so going back to the loss cone we see over here. So this part on top and on the bottom means that the particles are trapped. And there are physical parameters that constrain this entrapment, which is the magnetic field as well as the pitch angle. So that's how we saw that once we play it. Give it a sec. I think. Wait a bit. Okay. So here it's passing as we saw before, it's within the loss cone. So the thing is that Okay, this is an ideal case. Now, what happens when we have a lot of particles within this type of device? They interact with one another. It's like we have a room full of people and they will bump into one another. So there's a chance of particles being pushed outside into the loss cone and it will get lost. So we need to divide. So that's one of the main reasons of the motivation, closing the loop. Now, once we close the loop and put more coils on it, so two, we close the ends. When we close the ends, we need to recall that, oh, give it a sec. Okay, so when we close the ends, we're gonna see that these over here, these blue circles are the toroidal field coils. What do I mean by this? These are electromagnets. Similar like before, we just had two electromagnets, but now we align a lot of them in the shape of a donut to keep the particles going around. Now there's one thing that goes on. One issue is that if we're using electromagnets, the magnetic field is not uniform within this electromagnet. So what happens? If we have a non-uniformity in the magnetic field, that means we have a gradient in the magnetic field. So as we get closer to the coil, let's say the coil is right here. If I stand right here, the magnetic field is going to be strong. If this is the coil. As I get further away, it gets weaker and weaker. So that means that there will be some particles that are following lines that are not as strong as these. This gradient in magnetic field will also make the lines kind of move outwards. And as we move outwards, we create an electric field. With this electric field, we then have a different type of current that pushes the particles up. So we cannot just close it and add more magnets. We need to think about another way. Okay, how do we really prevent the particles from moving upwards? So going back to the presentation, here is the open field lines. So the end losses, then we close it and particles can circulate around the ring. And particles drift vertically because the toroidal field is not uniform. It's impossible to have a uniform field. So these separated charges create this electric field, and this electric field will lead to a different type of current that pushes the particles up or down, whether they're positive or negative due to the Lorentz force. Now, the solution is to twist the field lines. Now, how do we twist them? Any guess? Anyone? Any guess? You can think about it. Okay. The answer is once we inject enough particles that are spinning around this torus, once we have enough particles spinning around, we generate this toroidal current. So I will use the word toroidal, meaning it's going around the donut. Thinking about the tokamak as a donut. So we're going around the donut. This is the toroidal direction. And if we're going like around the short way of the donut, so this would be, let's say that this one, if we connected this guy to here, this part would be the toroidal axis, and this part would be the poloidal axis. Now, if we have a current flowing this way, but in a circle, then we would generate a magnetic field in the poloidal direction. And this magnetic field would interact and actually create a helical field lines once it interacts with the toroidal field coils. Okay? So that is one of the ways that we start to prevent this loss due to vertical shifts. So the toroidal field alone, curvature and gravity drift separate the charge, but the helical field samples both sides and averages the drift. And here, up here, we have some of the mathematics. So here it's the toroidal magnetic field, and this is the poloidal magnetic field. So the toroidal magnetic field is going to be, how can I put it? Okay, perfect. Let's say the toroidal magnetic field are these red parts around me, right? The field is going to be the stronger at the center. As we go out, it's going to be weaker, right? But now we have plasma surrounding it. And that plasma surrounding it will make these helical field lines, which will help for the confinement. But there's still another thing. It still may shift due to instabilities vertically. So the plasma, even though now we have somewhat of a confinement, we need to have a way to control how the plasma moves vertically, not horizontally. Because horizontally, the boundary is already set by the toroidal field coils. So the coils around this way, the coils that generate the field this way. Okay? And the field generated this way is the one that may lead to the plasma shifting up or down, depending on instabilities that may arise due to the particle interactions within the plasma. So the tokamak idea is the toroidal field plus the poloidal field would equal to helical confinement. So we need 3 magnetic ingredients. The toroidal field coils, it's a strong field around the donut. So here we have the ether for reference. Okay. So here we can see that this part over here is the D-shaped part are the toroidal field coils for the design of ether. And as you can see over here, these would be the poloidal field coils. I will explain their use briefly. But the main current that helps for the confinement actually comes from the plasma itself that would be gyrating here around the donut. So we need to have a balance. And for this balance, I won't go too much into the detail because if we want to go into the detail, it's a whole magnetohydrodynamics course, and that's 1 semester to 2 semesters. Skipping all of that, we just have to know that there are certain mathematical conditions, such as the pressure balance. So as the plasma itself is gyrating, there's some pressure that's being created outwards. Pressure that's being created by the particles that want to escape. Now the thing is, we need to counteract that balance. And this counteracting of the balance leads to a state called equilibrium. Equilibrium would arise when the pressure of the plasma and the pressure and the magnetic pressure balance each other out. Now, as I know some people are from engineering background and some people are from physics background, this is ideal. So the world is not ideal, sadly. Apart from this, we see that pressure is a flux function. What do I mean by this? The pressure itself that's being generated, we see it come from the flux, the magnetic flux. So if we look at the center of, let me see, okay, not here. Let's go back to the simulation. Plasma current. Let me see, play. Sorry, let me just, okay, this is the best one, plasma current. Okay. So here, the plasma current produces the colloidal field, and combined with the toroidal field, these make the field lines wind helically along the plasma. Okay. Okay, so you can see that the particle will be shifting between the outward and inward part, because as we create this helix, the particles will be moving out and in. So there will be this horizontal movement in addition to this vertical movement of the particles as they circle around the torus. So with this, we start to have confinement. But how do we generate this plasma is going to be the next thing. And before, so, well, finishing the part of the flux. As we have this helical magnetic field from the center to the outward part, we're going to have different flux, magnetic flux. But under the conditions that we set, this flux is going to create a surface. So if we see the radius, now we're no longer seeing the radius like the center of the donut, but rather the center of the plasma. So if we look at it from the center of the plasma outwards, we're going to see that the flux is going to be different at different radius. And this difference in flux will lead to the pressure. Now, we know that this also flux surface here is represented by psi. So also the toroidal field function to measure the toroidal flux is also a function of this psi. And then to identify these closed field lines for equilibrium to occur, we use something called the Grad-Shafranov equation. I won't go too much into detail about what that is, but it's a way to analyze how to balance this plasma pressure pushing out compared to the magnetic pressure confining it. So that's the main thing. We need to compress this thing because it's trying to push out. So this dictates how strong the toroidal field needs to be. Okay, following, how do we create this plasma? So we can think about a transformer. A transformer is sending a current down one coil and it induces a current on a separate coil. So on a coil right next to it, there's an engineering process behind that, but I won't go too much into it, but it's the basic principle of how a transformer works. So in here, one coil is called the central solenoid. So right in the middle of the donut, Wait a bit. Right in the middle of the donut, we will see that in here, there's this tube, and within that tube, there's something called a central solenoid. This central solenoid acts as one of the coils for the transformer. So I don't know if you've ever seen like isolated transformer. Maybe yes, maybe no. Or have you seen like a transformer opened up? Then you see that there's two sets of coils with the ferromagnet inside. And once we apply the voltage and the current on one of the coils, we generate a different one. Okay, so it's kind of like the same principle, but here, one of the coils is the plasma. So that's how so by doing a massive current change, like I'm talking massive is roughly, we'll showcase it in a bit, but it's on the order of tens of kiloamps in 1 second. So we have to dump a massive current very fast to be able to induce the voltage that will drive the plasma around the torus. So that's how we, oh, sorry. Okay. So that's how we, okay. So yes, that's how we start the plasma. So pretty much what we want to is to light a match, and this is how we're lighting the match through a process similar to the transformer. So we want to ignite the plasma and start to make it flow. Once it starts flowing, then we have different heating mechanisms. One can be neutral beam injection. So we send neutral particles in that are highly energetic. And these neutral particles will not interact with the magnetic field, with the electric field, but they will only interact kinetically. So it will be a kinetic transmission of energy. Another way is through electron cyclotron radiation heating. What is this? Now for the electron cyclotron radiation heating, it's which I'll explain a little bit the principle of it. It's pretty much converting the wave energy that we're sending in, typically millimeter waves, through devices called gyrotrons. So it's like a microwave. It's similar to a microwave, but just in a different range, right? But the cool thing is that once we inject these waves, we can enter with resonance with the motion of the particles within the plasma. So how are the particles in the plasma moving? If you recall, at the beginning I mentioned there's this gyro motion. This gyro motion has a frequency. So if we hit the resonant frequency of the gyro motion, we can transmit the energy of these millimeter waves or these waves that we're injecting in, and we transmit this energy into the kinetic energy of the particles through resonance. And that's a super cool thing, because in the opposite case, we can either give or take energy from the particles. So we can control this. And that's another heating method. And there are other methods of power deposition, but I will not go too much into the detail because these are the main ones. And I think in ITER, these are the ones that will be used. For the program that I am working on, for the project that I am working on, it's not going to be comparable to ITER. It's only a research device. And we do not plan to have neutral beam injection due to the price and due to constraints on export control from the devices that we actually need. So it's expensive, and a lot of people think that we will use it for bad things. So one thing that I have to disclose, the NBI absorption depends on the density. Of course, naturally, because if we're injecting the neutral particles, they need something to bounce off with. So through this bouncing, we're transmitting the energy from the neutral. Boom, it crashes into the plasma. It gives kinetic energy. So moving on. Okay. Let's go back to the simulation over here. Let's see if I have to reset it. Play. Here we see the transformer response. It's the live model. Yeah, I have to reload it. Sorry, guys. This was more of an experimental lecture because I'm doing a live demo at the same time of doing the PPT. So I wanted to make it this way so it's a little bit more easier to visualize the concepts. But it's a little bit constrained by my equipment because my main computer broke. So yes. So here we see the transformer response, which is the loop voltage over here. So the loop voltage means as we send current down the central solenoid, we have to see, oi, sorry. Let me reshare the screen. Hey. Wait. Meeting is being transcribed. Let me see. Let me stop share and reshare again. All right. Let me see. Maybe now. All right. So, okay. So this is a cross-sectional view of the, wait, let me present. You can go into full screen mode. Okay, well. All right. Don't worry. Okay. All right, we good? Okay, let me put hide over here. Wait, there's a little bit of delay. Is there a way to put it full screen? Or okay, well. All right, so we can set this and play. Mhm. Okay. Let's reset chapter. Okay, so here we can see how the yeah, okay, so here we can see how the loop voltage pretty much acted as a transformer, leading to the current in the plasma over here. But we see that this plasma current started to die out. So we weren't able to reach equilibrium. That means that the plasma current, as it goes down, right now it was, you can see 0.06 megaamps when it started at 0.5 megaamps. So this is 500 kiloamps for reference. So right now it's still not stable. Nonetheless, with this, We can also see how the PF vertical position, it should be this one. On PF vertical position, it should be vertical, they're opposite, sorry. So this one and this one, we see axis displaced. We control the vertical positions of the plasma. Finally, we go to the last part. I see it's almost time for the 5 minutes left. Yes, yes, yes. For discussion. Yeah, okay. So right now, this is the last part. So here we can see how the actual tokamak would look like if we're giving it power both from NBI over here, neutral beam injection, and the electron cyclotron resonance waves. So here we're using actually 3 heating methods. One I did not mention that is very key to this device working and heating up is the ohmic heating. So the ohmic heating would occur once we have enough, once the density is high enough and the current is high enough, we have particles colliding with one another, and this collision would lead to this thermal energy to heat up the plasma. So that is the approach that we're going to take in first. And since we only have 5 minutes left, yes, I will give this to everyone to play with and you can study it. But I'm at slide 14 of 36 slides. So don't worry. The next part is very quick. So what is a tokamak and how do we build it? Let me wait a little bit for it. Okay, yeah, it's my share. Share. So the next part is going to be really quick. Now, I've explained how the basics of the tokamak works. Now, I will briefly go over my job, what is the part that I am doing now for the development of the tokamak in Taiwan. And for a tokamak, it's not just plasma physics. It's also pulse power, sensors, synchronization. You have to do data analysis. And you also need to have some knowledge of control systems. So it's a very, very complicated thing. And a lot of people have to collaborate together to make this work. So first connects the magnetic geometry to a real machine. Oh, let me put this. And these are the parameters of the tokamak that I'm currently working on. And we expect to have the first plasma either this year or next year. The first plasma will not be a plasma that we can sustain and create energy from. It's just to ignite a plasma. So pretty much just like strike a match and see the fire, and then it will burn up like that. So right now, one of the testing platforms that we developed is called the mini tokamak. And it's pretty much a tabletop mimic of an actual tokamak. This is for testing purposes. So it's a testing platform for lower energy driving, just to as a proof of principle that we can use the equipment to drive the coils. And we can implement some diagnostics in it, even though it's not finished. So there's also the coil driver issue. So for the coil driver, we need a hardware that can handle several kiloamps. Like for example, the magnetic field that we're generating, if we want to generate like 0.4 Tesla on 16 on on the device that we are currently using, we need 7,000 amps. Now, to get that current, we cannot plug it into the wall. We take the whole grid down. Now, how do we generate such a large current? So we need to use a very interesting way that employs fast switching, and this fast switching of the current makes for spikes and EMP noise, and we also have to implement safety. So right now, the thing that I have designed and tested is this guy. So this is a single module that we're using for driving the current. So how are we driving the current? I don't know if you guys have ever played with a battery, a car battery, and you join the ends. I don't know if anyone here is like that, or maybe not. Yeah. So you see, when you short it, you see a spark, right? So the thing is, a car battery, it's only 12 volts, but it can give up to 800 amps. So what we're doing is we're using something similar to a battery. We're using supercapacitors, and we are using PWM, which is called pulse width modulation. So PWM it's kind of like a switch. So when we close the switch, current can go through. When we open it, current cannot go through. So the thing is, here we have the supercapacitor bank. When I mean supercapacitor bank, it's 1.12 farads. For the engineers, you can have an idea of how big that is. Typically, the components that we use are microfarads, nanofarads. This is 1.12 at 750 volts. So, and we have two in parallel. So we have 2.24 farads. So for that, we actually need a filter to protect an LC filter to protect the supercapacitors. We also need a snubber circuit to protect the switch. I won't go too much into detail, but the way we generate this current is that we charge these capacitors, and this capacitor acts like one of the car batteries. So when we short it, we see current going through. All right. So to control the current, we use something called PWM that is kind of like a mixture of opening and closing of these switches. So right now, for most of the smartphones, the way you control the brightness of the screen is through PWM, because the frequency is so fast that the human eye cannot see it, but the intensity of the LED will be lower based on how long we close the switch. So the longer we close the switch, the higher the current. The shorter amount of time that we close the switch, the lower the current. So that's what we do. And since the inductance of the load is pretty large, we can see over here, we can just focus on the black curve. The black curve is the current, and we reach up to 1.5 kiloamps. This is per module. Now we have 4 modules in one rack. So 4 modules in one rack was the thing that I built. Now the rack is not just a box, it's the practical system that turns the tokamak magnetic field design into an experimental pulse, because now we have 4 of these modules that can give 1.5 kiloamps each, just sending it out. So personally, the modules are rated for a little bit higher, so we stress tested up to 7 kiloamps. If we think about it, 1.5 kiloamps times 4 would be 6. But once we did the test, okay, we pushed it up to 7 just to see if it works. It still works. Now the results to highlight, okay, four current drivers connected in parallel reached a current higher than 6.6 kiloamps. Now over here, you can see a flat top. That's where I will talk a little bit about the implementation of AI. This is another circuit that I made. We can just skip it. This is the latest one that I made. It's pretty much the same thing. They're all doing the same thing. This one is just to make a positive and a negative current through an H-bridge configuration. So we can control if the current flows this way or this way through a special scheme. Now, diagnostics create a large, messy, high-value data. So I think for the experimentalists in the room, you have worked with an oscilloscope. And when you're saving data from the oscilloscope, you tend to have very large CSV files. Or at least for me, the CSV files that I have are of one shot, it's up to 50 megabytes. And that's only data. So it's kind of like 8 channels and 1.25 million points per channel. Now Excel cannot handle this. So personally, I was tired of having to write my own code. Well, I guess I was lazy and I don't want to rewrite a code if I go to a new place and I don't have my computer with me. So I just made a program that can just do it for me. And now that's what I want to get to with AI. Well, measurement reality saturation is not the same as missing data. Over here, we can see that this data, the data in black, was actually very, very noisy. We realized that the source of the noise was one of the components that we removed, and then we had this type of really nice curve. Right here, this, I don't know if you can see it well, it's 6 kiloamps. This part is 6 kiloamps, reach up to 7. So here comes the reason. A scope analyzer or scope studio. Why I built it? Because the oscilloscopes have a massive, they give out a massive data, and I need to have a quick way to verify my experiments. The main reason for this was, it's a little bit embarrassing, but when I went to do the first experiment on the actual reactor, the facility didn't have a single working oscilloscope. Now, for an experimentalist, you can imagine how frustrating this is, because you go, you do experiments, and then you don't have any data. So you have, it's like you didn't do anything. Or you did something, but it's just a claim. You need to show the evidence, right? So the reason why I built that is mainly just to analyze the data quickly, and then I added more features into it. So over here we can see this, the blue curve is the actual measurement, but at this flat top, we see that we saturated the current monitor. What I mean by that is we exceeded the rating of the current monitor. So now what do? We know that we exceeded it. So now we need to reconstruct the actual curve using physics, or actually using engineering, because it's just a simple RLC discharge. So we use an RLC model to integrate it into this. And that's the main thing that I built. And I have it right over here. So for this type of data, by the way, this program, I'll upload it to the drive as well. So any experimentalist, you can just use it. Just however you want. It's, yeah, once you grab it, it's yours. So the thing is, let me clear the filter. Okay. So we see over here, we see these massive spikes, but these spikes are due to switching, because every time that we switch the current, we have, in a circuit, we will have a voltage spike. The voltage spike comes from the inductance of the component times dIdt, the change in current over time. And right now we have a very large dIdt. So we will have a very, very large spike. But these spikes sometimes only affect the data. They are not real. So it's due to the electromagnetic pulse propagating through the ground, affecting the measurement instrument. But it's not the real current itself that is being affected. This is the interesting part. So then I said, okay, let's just put a 15 kilohertz filter. We can filter the data. The reason why I can filter the data here is because I use 2 separate devices to see if the pulse was actually real or if it's just noise created from the EMP. And once we do this validation that it's just noise, then we can do the numerical filtering. Otherwise, we cannot. Okay. So here, the reason why I did this is to make, okay, following nature communication guidelines, and I made this program to make a figure that can be publishable. And the full version is on GitHub. You can download it. The full version actually includes a local LLM that can help you develop the tools that you need. So what students should learn from the AI example so far, the whole simulation that you saw me giving to you of the tokamak, from the magnetic mirror to the tokamak itself, was developed with the AI. Now, if we're going to develop something with AI, we start with a real measurement question. We have trusted, invalid, and censored regions for the data that I showed. We choose the simplest model for the physics, a model that we understand fully, and then we verify the code generated by the AI. Because we have to understand what we're asking before we ask it. Now, this is the thing with the AIs. The AI is just an LLM, is pretty much just an autocomplete on steroids. So it does not think, it does not understand. It can do inference, but it's different from understanding. So it still needs the human validation to be able to be implemented. So we use AI to implement, test, and document faster. For this, no physics is needed. We do verify the numerical integration, numerical differentiation, the low-pass filtering with numerical analysis models. So for that, an unsafe shortcut is to make the curve look reasonable. But the scientific use is to expose the assumptions, the uncertainty, the residuals, and how it may fail. So AI accelerates the workflow. The scientific claim is tied to the diagnostics, equations, and human validation. Especially, the AI cannot do validation for you. This is something I have to be extremely clear. You have to understand the physics that you're asking it to simulate before you ask it to simulate. Otherwise, it can do something that you may not understand. And there's a saying, you don't know what you don't know. What do I mean by this? If you don't know, if you don't understand the physics, how will you know that the physics is wrong? How will you know that the energy is not conserved potentially in a model that, or whatever type of model that you're working with? You need to completely understand it before you use it. If you can develop it by yourself, it would be actually better, but at least you have to have the understanding of the underlying physics before implementing it into AI. So how to use AI without losing scientific control? A good AI prompt structure would have the context, the constraints, the expected output. We also always do a test case with one case that we have validated ourselves and we know the effect of it. And we then apply the validation. So the validation checklist, we need to check the units and sign convention, because sometimes the AI it doesn't do it on purpose. Hallucinations are not things that are done on purpose. Hallucinations are mistakes. Mistakes because the model sometimes fails. And it fails in ways that sometimes are predictable and sometimes are a little bit less predictable, especially with the newer models. They can seem very good, but at the same time, for certain tasks, you cannot fully trust them. So, for example, for the scope analyzer, we need to leave the raw data unchanged. So what it does is that it loads the data onto the RAM into like kind of a virtual environment. It manipulates the data in this virtual environment, leaving the original data untouched. And then afterwards, we can export this new analyzed data, leaving the original data untouched. This is a key point, because if the program accidentally modifies your data, sorry for the language, you're screwed. You have to redo the experiment. So you need to keep you plot the raw and process data signals together to make sure that everything is going okay. And you keep scripts, versions, and source file hash. So kind of like you keep a log of the progress that you're doing in whatever project that you are developing. You need to keep a log of every step that has been done. So what typically, if you want to implement Codex or Cowork or Claude Code, you should ask it to have a markdown file that logs every single change that it has done. It's going to be a long list, but it's one where we can identify any potential point of failure in a simulation. And the limits and risks of AI, okay, what can go wrong? We already went through it, invented explanations, silent units, sign mistakes, overfitting to one data file, or unreviewed code from raw data. And how do we protect the science? We do version controls and tests. We keep the immutable raw data. Immutable means unchangeable. So that file will have to be there. And then we generate another file post analysis. And we have to do independent physical checks. And we also have to implement some schemes that prevent the document assumption and the failure. So this is the take-home message. Fusion needs a magnetic bottle because hot plasma cannot touch the wall. Otherwise, the whole thing blows up. Well, it doesn't really blow up. It melts and then shuts down. The tokamak is a toroidal magnetic bottle with twisted field lines. So it's just like a bottle that connects back to itself. So it's a little donut. And real fusion research depends on engineering, coils, drivers, diagnostics, and data. And AI is useful when it helps build transparent and validated tools. Transparent, I mean that you cannot ask it to build a model for you that you do not understand yet. What do I mean by that? If you want to implement, for example, there is new advances like physical input neural networks or physical input neural operators or differential equation neural nets. This is the frontier of AI research on physics. But it has to be transparent. Now, the thing is, a lot of these models, such as the deep learning model, deep learning is still a black box. We still have to understand the physics behind it to make sure that the model works. So, sorry for the long talk. It went a little bit longer than I expected. I hope I didn't bore you. I hope you learned something. And any questions?
Okay, please give applause to our speaker for the very interesting talk. And then we have, around like 10 minutes for question. Okay, please.
Thank you. Great presentation. I want to verify first, like what you do, what your research in your current research. Is it like, you know, what I get from your presentation that you like design for Tokama? It's like a new.
Okay, so what my job is to, you see the coils, right? Okay, so the coils need current to produce the magnetic field. My job is to build the power supply that gives that current.
Okay.
Yeah. So the thing is, right now there was one new modification. So I have to be clear and I have to be honest. I'm not doing science. Right now, I am not doing science. I am more
Engineering.
Not really an engineer, because an engineer optimizes. I'm more like a technician, because we're still at the phase that we're developing the device prior to doing research. So as an experimentalist, if you don't have a device, you need to build one.
Yes.
To be able to do experiments. Yes. So right now we're still in the phase of building the device. So we are going to perform the first experiment later this year. And that will be the first, you could say, like actual science that we're doing, which would be studying the startup process of the plasma within our tokamak. So to answer a little bit more your question, right now I'm designing the power supply for the coils. The new thing that came in with my research is that I had to use a different circuit than the conventional circuit due to export controls on certain equipment. So what we use to actually control the switches, it's a high power switch, kind of like the light switch, but it's a transistor. A transistor is a switch. So I use a transistor called an IGBT. An IGBT is an insulated gate bipolar transistor. Now, to make it simple, it's like we have this flow over here. Let's say that this is a tube and water can flow down. But inside, there's a gate. So how do we open or close the gate? We apply something that is called a gate voltage. That is a very small voltage. So once we apply this very small voltage, the gate will open. Yeah.
Okay. I may elaborate why I'm asking the question. I currently work as I'm not saying computational physics.
Okay.
I working on machine learning, so I looking for something that we can maybe elaborate about your research. So I am a little bit curious. Is
Yes.
there any data or something that maybe we can work together? I thought when your presentation, maybe we can maybe I can help maybe develop a new model for maybe a tokamak right now that you say that have several loss energy or something. So I'm asking that is there any data available for me so I can explore for more?
Yes, there are several open data sets, and there are some. Okay, so the research so far in application to tokamaks have been through, I think, if you're familiar with machine learning, I think you may be familiar with PINNs, right? Physical input neural networks.
Yeah.
Okay.
We can say that.
A little bit,
Yes,
right?
yes.
Because we're implementing for physical input neural networks, for all of the neural networks, we know that the reason why they work is that they're a universal function approximator, right? Yes. So, and we approximate it by measuring that loss function. We want to minimize the loss function, right? Okay. So if we want to involve physics, we put the physical constraints into the loss function. And this would make the model more physically real. Yes. Now, if we go one step further, there are physical input neural operators where we are not pretty much getting. So the issue with PINNs is that every time we solve a PDE, we have to have a certain boundary condition, right?
Yeah.
But the problem is that if we change the boundary conditions, we need to retrain the model because it doesn't know the solution. It only knows the solution for that boundary condition. If we change the boundary conditions, the model may no longer work. We have to retrain it, right?
Yes.
Okay. So then here is where the next step, has been relatively new, I think within the last 2 to 3 years. So it's more frontier research on AI application in physics, where you have like physical input neural operators or Fourier neural operators. I don't know if you're familiar with this or not.
No.
No. Okay. So that's completely fine. Don't worry about it. But you can take a look at it. I cannot explain it too well, as me myself, I'm also starting to develop the skills to be able to do research on AI implementation in physics at this level. But to give you a brief summary of that, what we're looking for instead of approximating a function, it's like we're approximating an operator. And if we approximate an operator, we can find the solution for families of problems. Because we no longer treat it as, we're no longer looking for the function, we're looking for the operator. Is that clear? I know it takes a little bit time to process.
Yeah, I think, yeah, I think I have to reread about the PNN. But my question is there any data available in your lab? You know, it is specific for maybe.
Oh no, we don't have data because we haven't
so it's
done an experiment
public
yet.
Oh, okay.
And
yeah,
if you want to collaborate, of course, I'll give you my email. I can also give you collaboration with the High Performance Computational Center in Taiwan. That they are another subgroup that are working on the frontiers of implementing AI into the tokamak. So they're also they also have many open data sets, and you can start with I'll give you my email and we can engage in correspondence, and then I can also give you the references. And also, if you're interested in the future, if you would like, are you an undergrad student or a master student? Sorry,
I'm a master student.
Master student. Okay, well, if you're interested in a PhD later on and would like to pursue this area, I could refer you to the people in there. Yes. Because right now, yeah, we welcome. If you have the motivation, if you're interested, more than welcome.
Thank you very much.
That goes for everyone. That goes for everyone. If you're interested in the topic, yes, I think I will talk with the professor. I'll give my email, and then you can distribute it, and as well as the drive file, so you can download the models that we saw today and the program for the experimentalists in the room to test it out and play with it as you want. So yes, we can engage in correspondence, and I can give you some of the basic references, papers to understand kind of like what the models are doing. And then we can start developing models together, and yeah, we help each other out.
Okay, thank you very much. Thank you.
Mas siapa namanya? Mas apa?
Samuel.
Bimbingan siapa?
Pak Iman.
Pak Iman. Oh ya, nanti bisa kontak saya untuk bisa ketemu.
Terima kasih banyak, Pak.
Good. I think for one very quick question. There is someone to us. Okay, please.
Excuse me, I want to ask, what is the frontier in the fusion technology? Why we can achieve the technology yet? What is the problem with the fusion?
I think it's with a fusion reactor.
Yes, I'm processing how to give you a clear explanation, so sorry for the pause. Okay, so the largest constraint is the engineering constraint. We haven't found a way to be able to confine the plasma, which is hot enough for long enough to generate more energy than what we put into it. This is the largest constraint. Now, the thing is, so ITER is the International Tokamak Experimental Reactor. That's what ITER stands for. And it's in France. It's supposed to be the largest device for fusion research in the world. Now, it's a multinational collaboration. There's a lot of politics involved, and there's a lot of delays involved. But the main thing is that we think that building a larger reactor may solve the problem, but we're not sure. The main constraint is engineering. The physics is already there, but how do we build it? How do we control an unstable plasma? Because once we have the plasma itself, think about it like water flowing. If you have water flowing and you have some turbulence, like some perturbation, sometimes these perturbations grow and they grow into an instability. And these instabilities just cause the whole plasma to turn off because we no longer have the condition to sustain the confinement. And once the confinement is lost, actually some of the particles escape and hit the wall. But those are the largest constraints so far. Engineering, and we actually believe that making a larger device may work, but we're not sure. It's a huge bet. It's like a gamble. We're hoping that it might lead to progress. And a device of that scale will allow us to understand fusion much better because so far the devices that we have are very small and small in comparison to ITER. So we think that potentially at a larger scale, we may be able to sustain the plasma a little bit longer, long enough to start studying equilibrium conditions, because so far we have not achieved equilibrium conditions. Equilibrium, I mean that the plasma is flowing, the plasma is heating up, and the heating up is controlled, and that heat or the emitted neutrons then are sent out, they heat up water, the water then turns into steam, and the steam produces electricity. We haven't even gotten to the point where we can make steam yet. I'm sorry for being a little bit pessimistic, but it's not to be pessimistic, but more realistic. It's not to say that no progress has been done. A lot of progress has been done, but it's not as simple as fission. And fission is, I don't know if you know Pandora's box. They're in the mythology. Fission is like once you open it, you cannot close it. You have to bury it underground under like tons of concrete and put some lead on it to prevent radiation to come out in case something happens. So that's the main reason why, and also the nuclear waste. Nobody wants the nuclear waste next to their home, even though it may be safe. But still, nobody wants to have that next to their house. Yeah. Okay. Does that answer your question?
Can I ask another question?
Of course.
Why are we using donut shape tokamak rather than linear accelerator?
Oh, because the particles would the linear accelerator that I showed at the beginning, due to the particle-particle interaction, there's diffraction, and particles tend to get thrown into the lost cone. So they just tend to end up escaping. So the reason why we want to close it into a donut is because it cannot escape from the sides. Because if it's a donut, it can't really escape. It's trapped. Meanwhile, the other one has more, how can I say it? It's like more room to escape. Yeah, that's the motivation for the donut shape. Also, most of the common fusion devices are donut shaped, but there are some like twisted donuts or a squished donut, but a lot of them just look like a donut.
Yes, I'm confused with the donut shape because if we have magnetic field and plasma, they will move in the same direction, right?
Yeah.
So I think the collision is minimized if we have donut shape because the particle will move in the same direction.
The collision will be minimized, but there's always, the thing is, okay, that's ideally, but once we have the helical magnetic field lines, we create these nested surfaces. So, but the problem is that sometimes these field lines move and they merge. So it's a process known as magnetic reconnection. So a field line might break due to some turbulence, and then it connects into another one. And in this process of reconnection, a lot of heat is also generated. So we also want to take advantage of that to heat up. So apart from the particle-particle interaction, we also use the neutral beam injection to inject kinetic energy into the plasma, as well as the electron cyclotron radiation heating, which is, just think about it like this. The microwave is designed to 2.45 gigahertz because that's the resonant frequency of water, I believe, something like that. It would make the water molecules move, and then that heats up the food, right? It requires some moisture within. It's something like that. What we want to do is we want to inject waves that excite the particles, and we transfer the energy of the wave from the, the b squared over 2 mu. I think I'm sorry, I forgot the name right now, but yes, we want to convert the energy of the wave into kinetic energy through the resonance frequency of the gyro motion. So then that's one of the main heating mechanisms. Right now we're trying ohmic heating for the startup, but then in the future we will introduce neutral beam injection. Yes, to add to the kinetic energy within the confined plasma. Yes.
All right. Thank you. I already understand why we use linear donut shape accelerator. Thank you.
Okay.
Is there anything that any doubt or any other question or any doubts? Feel free to ask anything.
Okay,
It
yeah, I
has
think
basic-
because of the time is up, then I think we have to close it. But
okay.
I think Jean will be around here still
Yes.
a couple of hours maybe. Then if you like to discuss, then you can just approach him around this this building, and maybe you are also still in Indonesia until 27th.
Until the 28th.
28th until 28th. So
Until 28th, but some days I will yes.
you will leave.
Because I'm not staying in Yogyakarta.
Ah,
Yes.
okay.
But
Okay.
I can leave the email, and they
Okay.
can completely. Anyone can email me for any question, any topic, any interesting collaboration.
That's very nice.
Anything that would be, yes.
Now we
that
have
would be
very
nice.
strong collaboration with Taiwan. So actually, so we visit Taiwan several times. So maybe next time we will also visit you guys. And yeah, I think just keep contact with him if you are interested with his research. And yeah, I think we have to finish somehow because. But thank you very. It's very nice and interesting talk. So before
Sorry, I didn't realize the time.
okay, okay, that is nice. So before we close this session, I would like to invite Dr. Dwi Satya Palupi. She is the chairman of this our research group. She is working in the fission and fusion and something else like that, something like that. So please, Bu Palupi, and hopefully you like to receive and what certificate, just like.
Oh my God. so